So hi, my name is Shreyas and I'm from the University of Pennsylvania. I work at the GRASP Robotics Lab and I'm going to be presenting DFuseNet, which is the overall problem statement is trying to combine RGB and sparse depth measurements and come to an upsampling of a really dense and accurate depth map. So I think this whole LiDAR versus RGB has been somewhat controversial over the last 6 months. And by controversial, I mean Elon Musk made a tweet and then everybody got rattled by it. So I'm here to tell you that, at least for now, let's try and use both of them to work together. This is the only picture I could find which had a cat and a dog that looked like they were working together. But I feel this is an accurate description of where we are in LiDAR space right now. So what you can see is, what we usually have is sparse depth from a LiDAR, like a Velodyne 16 beam or a Velodyne 64 beam, but we have access to this high resolution RGB imagery. Is there some way we can take both of these and get really dense depth information for a variety of tasks? I mean, being in a robotics lab, we talk about navigation, but in self-driving, we have similar problems. So this kind of task has got some popularity over the last, I'd say, 1.5 years. They've been put into different categories with different names, like depth completion, image-guided depth upsampling, and just RGB and depth fusion. So I'm going to quickly run through the actual network design that we used. It's a pretty simple convolution neural net design that takes in sparse depth and an RGB image. One of the things we decided early on, just looking at the available research at the time, was that it was a better idea to use two separate channels instead of concatenating them. One of the key things to keep in mind is that depth and RGB are very different modalities. Even though you can make them both images, but the actual values, the experiments doing like a naive concatenation with the separation kind of confirmed our theory that it's better to separate them and learn individual features and then concatenate these features later on. At least at the time of writing this paper, the Kitty depth completion benchmark came with a paper that proposed sparsity invariant convolution neural networks, which basically propagated a mask along with the convolution on sparse measurements. We did try that multiple times, but we instead used a much simpler approach. So we just take the sparse measurements and do a really naive filling. So you can just run your favorite morphological operator and nearest neighbor filling of your depth map, and then plug that through. So that, with this, you don't really have to use any fancy sparse convolutions. And we show that you can get really competitive performance with the same thing. We did a late fusion. I think some people call it mid-fusion, but basically we concatenate the two modalities after we kind of feel that they've extracted relevant features. And we use a multi-scale decoder to try and get this hierarchical representation before we finally regress to depth. The actual training loss was a combination of 3 different losses. So the Kitty depth completion benchmark is evaluated on RMSE. So an L2 performed the best if competing on that benchmark was priority. But we noticed L1 resulted with just nicer looking images. It's just something to keep in mind. One of the things we added was, so if you know the Kitty data set, you know that there's stereo data available to us. And the problem with just LiDAR is that you're usually missing out on information here. And this is a really extreme example. I had to look through all of the Kitty data set to find something extreme, but there was a bridge here. And if you have a really big truck, you run a risk of just driving through it because you don't really know what's here. But if you do a basic stereo matching, you can kind of get coarse depth here. So we calculate this depth only during training, and we add this as another supervisory signal to our training mechanism. And we're able to show that in places that most of these depth completion algorithms fail, we're able to actually predict some accurate depth values there, and similarly here. The last term is a pretty standard term for most people that do monocular depth estimation. It's just a second order derivative to kind of enforce smoothness and preserve boundaries. one of the things we saw early on was that we got really nice qualitative results. So you can see really clean edges here in our depth prediction, but our quantitative results weren't that great. Even at the time of our submission, I believe we were rank 11, and in the last 6 months, this benchmark has been so competitive that we're now rank 56. I think that says a lot about how fast this space is growing, but I still believe our results are quite competitive. So we had an RMSE of 1.2 meters. Sorry, that should be 1.2 meters, and so I just took a few snapshots from the Kitty validation set. So these are the kind of results that we're able to achieve. And one of the insights that I was really curious about is to actually measure, if possible, how much each of these two branches are contributing to the final depth map. So intuitively, you'd think that from an RGB image, you can get the really crisp, high-frequency edges, whereas the LiDAR is just giving you accurate depth at certain points. And so this experiment was basically setting the RGB branch to all zeros and using depth only, so you get this really blurred, blobby-looking depth map. And if you do the opposite, which is set all your depth pixels to 0 and just use RGB only, it kind of fires at all the high-frequency edges. And this is when you use both, so which kind of gives us the intuition that, okay, the RGB is actually contributing to preserve edges and preserve context among these edges, and the depth branch is just there to kind of tell you what is where, basically. And we ran our experiments on a few other data sets. One was Virtual Kitty. At the time, I don't believe a lot of other depth completion papers did test on this data set, but we achieved some pretty compelling results on Virtual Kitty. We also tested it out on NYU depth. Basically did the same thing, but here it's a little different from using LiDAR, because the range of values here is between 0 to I think 15 meters, whereas on Kitty it can go all the way up to 100. We also did a small experiment to see on NYU depth how many points you actually need to get the kind of accuracy we were achieving, and we noticed that you quickly plateau. So here it's the percentage of total of the image resolution in the number of sparse points that you need. So at around 0.5, you were okay. Another quick experiment that we did was to see how well our model would generalize. So if I train my network just on Kitty, could I learn to do depth completion inside my living room? And that's what we tried here. So this shows a model that was trained on real Kitty and then tested on Virtual Kitty and tested on NYU depth. Quantitatively, the values weren't that great, but qualitatively, the depth maps look like they make sense. The reason why quantitatively it was a bit off is because the maximum depth range that you're getting sparse depth from both the data sets are drastically different. So Virtual Kitty goes all the way up to 655 meters, which I believe is the sky, and NYU depth has around 12 meters. So another kind of fun project that we decided to do was, let's collect one of these data sets of our own and see how well a model trained on Kitty would actually perform on like the roads of Philadelphia. So my colleague Ian is here, who helped us build a calibration system that calibrated an Ouster 64 beam LiDAR to Stereolab Z camera, and we just drove around Philadelphia for like a couple of hours and collected our own data set. We were able to get pretty good calibration and overlap between the sparse depth measurements and our RGB, and we tested it out on like the Philadelphia data set, and it did pretty well both quantitatively and qualitatively. So we did release this as a small subset. We call it like an extra validation set. I wouldn't really train a network on just such a small data set of images, but if you want to just test out your model to see that it generalizes, it's available to be used by the community. So just a quick overview, all of this has been made open source. Our models, our networks, and this data set is available to download. And yeah, I'm happy to take questions now.